The oil platform, which overturned in less than 15 minutes, is now beginning to break up, and bodies can be seen floating underwater. 38 bodies have been discovered, and as further bad weather threatens the area, there's little hope for the 99 men still missing. As divers tap on the giant legs of the upturned rig for signs of life, underwater television cameras are sent 90 feet down to scan the living quarters below.
This oil platform cost millions of pounds, but it was blown up deliberately after capsizing. However, this is not the final chapter in this major disaster. Now the investigation begins. Why did the structure fail when it was built to withstand the huge forces of the North Sea? Which critical component was responsible? Was there a fatal flaw, or was the wrong material used? Were the safety factors too small? It's up to materials engineers to find the answers to questions like these. But what is materials engineering? One aspect is the microstructural assessment of a whole range of materials at magnifications up to 50,000 times or more. There's the making of new alloys, such as the molten titanium alloy shown here. The assessment of electronic device materials. The use of X-rays to examine crystal structure. The response of complex polymers, such as this plastic netting, to stress. Or surface treatment, such as plasma nitriding. These are just a few examples. In fact, materials engineering covers all aspects of the manufacture and properties of materials. A sophisticated and specialized world, the foundations of which are in the basic science of the school curriculum. Let's see how materials engineering courses at universities and polytechnics equip students with the knowledge and experience to become a materials engineer. Take welding, for example. After the Alexander Keelan disaster, materials engineers were able to show that a support leg fractured due to a built-in crack in a welded joint. The job of the materials engineer is to eliminate such defects. In an environment such as this, perfect welds are essential. Oil from this rig travels hundreds of miles to the terminal along the seabed. It's carried in pipes which are welded together and fed into the sea. Manual and automatic welding operations are carried out to build up thick, strong welds. And then comes the search for possible cracks. It's rather like X-raying a broken bone, but in this case, a source travels along the inside of the pipe, and the film is wrapped around the outside. He knows just what to look for, but there will, of course, be no second chance. Students learn about welding as part of any materials engineering course.
With conventional welding, which produces a rather broad molten zone, we see that in this particular case, and to weld thick plate normally requires several passes, which of course is a slow process. In this particular case, the plate is being welded by two passes, one from the top and one from the bottom, but in other types of arc welding process, even more may be required.
To examine the fine detail of a weld, it's necessary to cut through it, polish the exposed surfaces, and then etch. The structure of the weld may then be examined under a powerful microscope. A recent development in welding is the introduction of lasers. This modern technique enables a strong but narrow weld to be made using a single pass.
Here you see a weld which is remarkably narrow. It is, of course, a fusion weld. In this respect, it is similar to arc welding, but the particular feature of a laser weld, arising from the fact that the beam can be focused, then the weld can be made extremely narrow. The other consequence of this is that it allows of great penetration. And we have here some indication of the penetration in terms of the depths of the weld in relation to the power density. The main restriction on the power input is that it must be kept below that level, which will volatilize the metal.
Because lasers have immense power, they can also be used to surface harden engineering components, for precision wood cutting, to cut steel plate, and to drill minute holes, such as in this jet engine component. Lasers for this type of work are large, complex pieces of equipment. But here is a semiconductor laser attached to its optical fibre. Great numbers of these are used in the telecommunications industry. If you're doing physics at school, you'll already know how a laser works.
So I think that that's all that I need to say now about stimulated emission. It's a very difficult idea. The important thing is that it relates back to the ideas here, where an energy jump and you get a photon produced, and it also relates back to this idea of a laser being light amplification by stimulated emission of radiation.
The manufacture of electronic devices from single crystals is carried out under strictly controlled conditions in industry. The various devices are tested and examined using many techniques, including scanning electron microscopy. Here, whole circuits are being examined. During their training, materials engineering students become familiar with the principle and the operation of electron microscopes. The scanning microscope is being used here to examine a fracture surface. But what about the internal structure of materials?
Okay, what we're looking at here is a very thin sample of silicon that's thin enough to let electrons from this microscope go through it, and we're looking in particular at a region where there's a stacking fault. That's a region which is imperfect. And if you look here, you can see a set of fringes running along that direction here. I can follow them along by moving the sample as we're examining it, and the fringes appear to stop about there. But the reason they stop is not because the defect is finished there, it's because of the particular way we're looking at this sample. And I can easily show you that's true by looking at the diffraction pattern, tilting the crystal. Now we've got a different diffraction pattern there. Going back to look at that same region, and you can now see there is the original defect we went along. Instead of just that one defect, there's a defect going at a different direction, running up in that direction there. And the main point of looking at this sample in this way is to try and see just how perfect our silicon samples are, since it's the imperfections in the crystals that really control their properties.
Those defects inside the crystal were magnified 60,000 times using a transmission electron microscope. This type of microscope can also be used to analyze the chemical composition of minute regions of a thin sample. Here is a defect in a silicon sample. At a higher magnification, the electron probe can be condensed onto this defect, and the X-rays generated can be analyzed instantly. The display shows a high intensity of X-rays with an energy characteristic of iron. So the defect is a particle rich in iron. Here is another area where materials engineering plays a major part: modern aircraft, in airframes, cabin interiors, and engines. All engines need to work at as high a temperature as possible to be efficient.
Now, if we look at that equation, which is a theoretical limit, the important thing is that if we want our heat engine to be as efficient as possible, we want this fraction to be as small as possible. And the only way of doing that effectively is to make this temperature as high as possible so that the fraction becomes small. Divide by a big number and the fraction becomes small.
So efficient engines mean hot engines. Aluminium alloys cannot be used much above 150 degrees Celsius. Titanium alloys 550 degrees, and even nickel alloys much above 1,000 degrees. Clever devices like drilling cooling passages in the hottest running components still don't overcome the temperature limitations of metals. The way forward seems to be to turn to ceramic materials. These also offer another advantage over metals in that they are oxides or compounds which are chemically stable in the hostile environment of the jet engine. The trouble is, ceramics tend to be more brittle than metals, as well as having poorer shock resistance. In recent years, materials engineers have improved the strength and toughness of ceramics. These new materials can be exploited to great advantage, for example, in metal cutting, where the tool tip can get very hot indeed. And this conventional tool has just failed. Now let's see what happens when we use a ceramic tool. This one is alumina. Beautifully smooth surface, and the tip remains intact.
The first tool that we used was a cemented carbide, and it didn't last very long because you can see the whole of the nose of the tool and the cutting edge has collapsed. Now the reason for this is, at this high cutting speed, we generate a very high temperature between the chip and the tool. And under the stress which is applied by the chip, the cutting tool material has just collapsed. The second tool, however, was this alumina ceramic. Now this has a much higher high temperature strength. As a result, it hasn't collapsed, even though we've cut for much longer time, and you can see there's hardly any mark on the cutting tool and the edge is still perfectly intact. So at these high cutting speeds, the alumina, because it's got a higher temperature strength, is much better than the cemented carbide. But this doesn't mean that we could always use alumina ceramic for any cutting operation. If we cut at much lower speeds, or under conditions where the cut was interrupted, we'd probably find that the alumina ceramic would break, because the penalty we pay for this high temperature strength is brittleness.
Using polymer granules, an enormous variety of shapes can easily be manufactured. Here, the lightness of plastic or polymer is combined with the strength of glass fibre. This composite material is very efficient at storing energy and then releasing it. This jump in 1962 followed the introduction of glass fibre reinforced plastic vaulting poles. In a composite, we aim to get the best from both materials.
In last year's project, a student built the test rig and then he started to look at impacts on helmets of this type, in which you've got an outer shell using Kevlar fibre reinforcement. What I want you to do this year is to follow on with that work and look in more detail to the damage to the outside of the helmet. And the way you're going to do it is to take the information from the test rig and record it on this oscilloscope as acceleration against time. When you've recorded the data, then it's going to be taken into the computer and replotted as force against the distance by which the helmet liner is crushed.
Helicopters hang in the air relying on the strength of the revolving blades. These are subject to uneven, tensile, torsional and fatigue stresses. With the aid of computer design, the fibres can be incorporated in exactly the right directions to provide the required properties at each point. Once again, the materials engineer's predictions are realised as an engineering component. In this brief coverage of materials, we've looked at metals, device materials, ceramics and plastics. These examples illustrate the profound effect which engineering materials have on our daily lives. Within these few topics, you'll have seen the type of opportunity which this subject offers to your future. More information about materials engineering courses at universities and polytechnics can be obtained from the Institute of Metals.